Hello, everybody. Welcome to CFD College. I'm Ashkan, and in this channel, if you don't know, I present tutorials and training courses on CFD, Computational Fluid Dynamics, especially using ANSYS Fluent and related software from pre-processing to post-processing. Uh, if you wish to learn, if you like to learn CFD and become an expert in this field, this channel will guide you and will help you. So please subscribe the channel so you don't miss our future videos, and please share these videos with your friends if you find them useful, and don't forget to give us a thumbs up. In this video, in this tutorial, I'm going to talk about one of the most common and important errors in ANSYS Fluent. Uh, I think most of the users uh, faced have faced this error, which is floating point exception. This is the worst error in ANSYS Fluent. ANSYS Fluent have uh, ANSYS Fluent is a very useful software, and one of the reasons is when you get error, the error shows you what is wrong, where is the problem, mostly. But this kind of error, I mean floating point exception, it's a bit complicated because it doesn't tell you where is the problem, uh, and you need to check everything on your case to find the solution or the issue and fix it. So in this video, I'm going to talk about this error, and I hope you enjoy this video and it would be useful for you. So the first uh, types of reasons is a hardware, uh, type. Uh, it's really rare. I mean, it's not the most common reason for this error, but it might happen for you, which is not having enough RAM. So when you want to simulate a process using ANSYS Fluent, there is a rule. It's not, it's not a common rule, or it's not indicated in any, PDF or article or software help. But it's kind of unwritten rule, unwritten uh, law for simulating a simple fluid flow. I mean, by simple, I mean a steady state, uh, three-dimensional turbulent flow without any, complicated turbulence models. I mean, RSM, LES, or something, without any radiation models, multi-phase models, DPM model, and these, models. The regular fluid flow that you may have, for example, flow over an 8-4, or flow inside the pipe. For simulating uh, a project like this with 1 million cells, you need 2 gigabytes of RAM. So if you have a similar project or a complicated one, for example, a multi-phase flow with DPM, with radiation, and with two-phase flow, VOF or Eulerian, you need more. So maybe for simulating a CFD domain with 1 million cells, maybe you need 4 gigabytes of RAM. So the first reason maybe is having not sufficient RAM. So think about it. As I mentioned, it's really rare because when we have a complicated project and simulation, we usually use supercomputers, and this uh, you know reason is not for those situations because on supercomputers we have more than enough RAM. But keep this in mind that maybe you don't have enough RAM, free RAM, not occupied RAM, a free RAM on your system. But let's talk about the main reasons which are related to software. The most important one, the most common one is mesh. Grid or mesh is really, really, really important in CFD. It's more than 50% of your CFD project because if you have a good mesh, good by good I mean good looking and good quality with high quality mesh. If you have, if you don't have a good mesh, uh, you can't do anything. You can't do a miracle in Fluent, in ANSYS Fluent, or even in other software like Star CCM, like CFX. Mesh is so important in terms of accuracy and also convergency of your project. So if you don't have a good mesh, the project uh, possibly, maybe uh, have some problems in, convergency. And no matter, it doesn't matter how you try to uh, improve the convergency, for example, by reducing the URFs, by changing the solver models, by changing the discretization methods. Mesh is so important. And having a bad mesh with low qualities, for example, orthogonal quality, or the most important one, which is skewness in unstructured mesh. If you have a mesh with, for example, two or three cells having a high skewness near one, that may lead to a floating point exception. That may lead to divergence. So mesh is really important. If you get this error, the first thing you have to check is mesh, the quality of the mesh. You have to look at the mesh. If you have a three-dimensional domain, you have to look inside the domain, not the other boundaries. So mesh is the first and most common reason for this error. The second one is choosing wrong models. By model, I mean the solver, I mean the setup of the simulation, including boundary conditions, models, initialization, and solver methods. For example, if you have a mistake in boundary condition, instead of 300 kelvins, you may, uh, you know, apply, for example, 3000 Kelvin. This is a mistake and may lead to floating point exception. Or you may choose the boundary condition wrongly. For example, the combination of mass flow inlet and mass flow outlet is not good. In CFD, we try to have boundary conditions of different types, for example, velocity and pressure, mass flow inlet and pressure outlet, pressure inlet and mass flow outlet, or pressure inlet and pressure outlet. As you know, pressure inlet is a velocity type. So, a boundary condition. So, having a bad boundary condition is another reason for this error. Choosing wrong models. For example, the flow is turbulent, and you select laminar model. Or, for example, the turbulence model and the mesh and the Y plus are inconsistent. What I mean is you may select K omega SST and then you have a coarse mesh and Y plus is, for example, 2000. So this may lead to floating point exception. Uh, if you are working with um, precise models, for example, turbulent LES turbulence model or Reynolds stress model (RSM), specifically for RSM, you need to have a good uh, initial condition. So initialization is important also. If you have a, mm, for example, when you are working with RSM turbulence model, you need to have a um, first solution. So you have to run the simulation with, for example, K omega or K epsilon, depends on the RSM model you chose, and then use that simulation as an initial condition for the main simulation. So initialization is also important. Uh, if you have, for example, if you are simulating compressible flow, the value for temperature and density you apply in the initialization section is important. So you have to be careful about initialization. And the last one is in this page, on this page, is solver. For example, if you have a transient simulation, it's better to select piezo solver instead of simple. So the solver and the discretization, the order of discretization is also important. If you don't have a good quality mesh, you cannot choose, for example, quick or any other third order discretization for your equations. These settings have to be matched. Okay, so the solver choosing the pressure velocity coupling method between simple, simple C, piezo, and coupled. It's important and it depends on your project. For discretization order, you should choose second order most of the times, but if you get this error floating point exception, you can change it to first order and let the run, let the run goes for some iterations and then stop it and modify the discretizations to second order. What else? Time step. If you have a transient simulation, especially in multi-phase flow, it's possible to get this error, floating point exception. And most of the time, if you go back to, for example, previous time step and reduce the time step size and then run the calculation, you see that you can solve the simulation and you don't get this error. So time step is also important. And after the mesh, I think the most important reason is UDF. So if you have user-defined function in your simulation, make sure that if you have used some UDMs, memories in your UDF, you have to define the number of memories in the Fluent. Students and users most of the time forget that, and that leads to floating point exception right after you start the calculation. The next one is wrong UDF structure. Uh, Maybe there is a mistake in your UDF structure. Maybe there is a mistake in hooking the UDF. So you have the UDF and you forgot to hook that, or you hooked it in a wrong place, in a wrong section. So that's also important. Or maybe uh, you have some values in the UDF and the range of those values are strange, are aren't correct. So you have to double check that. For example, as I mentioned, you are defining, I don't know, a ratio, and then in the denominator, you have some variable and it's zero in some cells, and that leads to floating point exception. So you have to add a epsilon to the denominator. It's just an example. Or you are defining the velocity and you make a mistake. Another important point is that the unit of the variables in the UDF. For example, for the angle, it's radians. For I don't know, for velocity is meters per second. Uh, for length is meter. It's meter. So be careful of the units. Otherwise, you may define out of range values. And the last one is parameters accessibility. If you are, for example, using using a temperature gradient in your code, uh, you should let the run start without this code, because in the first iteration there is no temperature gradient. Or maybe you have second derivative of I don't know, velocity or temperature or UDS or something. It's the same for that, because at the first iteration there is no second derivative of any parameter. So just run the simulation for one single iteration and then compile and hook the UDF. So these are the main reasons I know about floating point exception. The most important ones are mesh and UDFs, user defined function. So if you get this error, floating point exception, as I mentioned, you have to check your case, check the simulation step by step from the mesh, the beginning point, up to the solver, and also the time step. Uh, and that is the only way you can find the problem. But as I mentioned, mostly the problem is in the mesh. So I would recommend you to start from the mesh all the times and check the quality, look at the mesh to see if it's good looking or not, check the boundary layers, Y plus, and the turbulence models with the mesh should be matched. Uh, you can't have a mesh with a large, for example, boundary layer, coarse boundary layer, and choose k omega SST, uh, which acts better if y plus is near 1. So that's it for this session. I hope this was useful for you. Please subscribe the channel and give us a thumbs up. If you like this video and if you think these tutorials can help you, please share these with your friends. Thank you for watching this video. And if you have any question, you can write your comment in the comment section below. Thank you again for being with us. Until the next video, take care of yourselves and bye bye.